Thank you so much. And thank you so much for inviting me. I'm very excited about this talk and about all the discussion that will happen afterwards. So yeah, I work at, I'm associate scientist at Fermilab. My background is in astrophysics. But let's say maybe the last 8 years or so, I've been mostly working on projects that leverage AI in some way. Again, mostly in astrophysics, but I'm also doing some projects related to neutrino experiments as well. And I wanted to talk to you about a couple of different topics. As you can see here in the title, these are topics that I don't know, I have been thinking about for a while because they are quite a present problem in science in most applications and probably in a lot of industry applications as well. So I usually start this talk with this slide, with something that I call the circle of doom, in some sense. But the idea behind this is imagine that you want to do, maybe you're a student and you want to do your first astro project and you want to leverage an AI model to do that. And people keep telling you that you live in a big data era for science. And I think that's definitely true. We have terabytes and petabytes of data, both in astronomical observations, as well as all the big experiments like colliders or neutrino experiments at Fermilab. But for your individual project, you might encounter a very small label data set, because while we do have a lot of raw data, we don't usually have a lot of nicely curated labeled data sets. And that in science is a very common situation, basically. So how do you even build your first model for your specific tiny task that you might want to tackle if you don't have labels? So in that case, you might choose to start training your models on simulated data sets. This is a very common practice in a lot of scientific applications. But again, unfortunately, once you train your model on your simulated data, where you control everything, you can create labels and you can have a nice curated data set, these models will very often not work as well as soon as you shift to the next real data that you actually want to apply this model to. So again, this is a very common problem. Obviously, I've had that problem, and hence I've started thinking about this issue in my career. Another problem that you will for sure encounter is uncertainty estimation. Maybe in industry, there are definitely, especially some risk-aware situations where uncertainty in your predictions are super critical. Maybe there are other ones where that's less important, but in science, every scientist will always ask, but where is my error bar? So again, UQ in all the AI methodology is like we're improving, but we are in many cases not there yet, at least for the level that like scientific research needs AI to be. So you'll encounter this problem as well. And especially if your model doesn't work, well, actually, I guess even if your model works perfectly, you want to understand why is it working. For science, again, this is crucial because it might point you to new physics, or it might point you to problematic areas of your data set and help you like gather better data if we could just interpret the model a little bit better. But again, even this is definitely not a data set that we would like it to be. And then once you're done with all of this, you might be asking yourself, well, okay, I have built some kind of model. Maybe it has some limits, but how does my model compare to other people's work and other models that people might have applied to a similar problem? And again, this is where we enter into the benchmarking problem in science, especially if you look at AI papers that are not just pure computer science applications, where you usually have a nice table somewhere in the text that compares your model to all the other models that people have applied to the same data set, and you can see which one is better or worse. In science, that's not very common, especially because we don't have a lot of those like benchmark data sets. So every research group will curate their own data. Sometimes data is not even public, especially like early in the kind of analysis period of some like new experiment. So basically comparison is also very challenging. And so all this that I've listed is kind of something that I think most people doing AI in science just encounter basically in all of their projects. So obviously this is a very broad topic and there are many problems, but because we only have 45 minutes, I'm choosing to talk about domain shift problem specifically. I will talk about all of these other things in that context as well, but the main focus is going to be about domain shift. And I'm, of course, going to introduce this a little bit further in detail, just in case you have not thought about this previously. So basically, this is my plan for today, to just kind of introduce the domain shift a little bit better and tell you what can we do about it. Maybe talk a little bit about uncertainty quantification in that context and where we are currently in kind of scientific projects that I'm involved in. And then hopefully I'll have some time as well for just to show you a couple of applications, couple of projects that we've worked on. Again, I will not have time to go into too many technical details, but hopefully we'll have time for that later on if you're specifically interested in one of these. So what is the domain shift problem? I already kind of mentioned this at during my first slide, but let me kind of go a little bit deeper with a couple of examples from just different scientific projects. So domain shift problem, as I said, is a situation where you have a model trained on one data set, but you actually want to apply it to a slightly different but still related data set. Because of the differences in properties between these data sets, and of course the complexity, especially of deep learning models, these models will very easily hone into various data-specific features, and because of that, they're not easily, you can't easily translate them to a different data set. So here I have examples of simulated and real data. The top row of plots shows a microboon neutrino detector at Fermilab. So we have a simulation where like a neutrino is entering the detector and then hitting a particle in the detector and just creating a shower of particles like protons, electrons, and so on. On the other hand, on the right side, I have an example of this actually happening in the detector. The bottom example is something a little bit more closer to what I usually think about on a daily basis. This is an example of simulated and real galaxies. So you'll be seeing a lot of examples of these simulated and real galaxies throughout this talk. But basically, this specific example actually is showing pairs of galaxies merging. So on the right, you have an actual observation from the Hubble Space Telescope. But on the left, you have something called the illustrative simulation. I'll have some slides where I go a little bit deeper in what this is. But it is basically a big, very computationally expensive simulation where we are basically evolving the universe from the Big Bang to today. And so you start from some initial conditions and then you generate all the structures and galaxies and stars and everything. And so in this simulation, also galaxies interact with one another. And so you can extract pairs of galaxies like these here. But the difference between simulations and real data can vary from very dramatic to very small, maybe not even visible to the naked eye. Like to us, they might look similar, but usually even in that case, this is not like good enough for an AI based model. So the differences, of course, in this case can come from, I don't know, missing geometry or parts of physics that we don't understand fully, that we're not simulating properly, or maybe it's just too complicated. And so we have to introduce approximations and some small choices here and there to just make the simulation run faster. This is the case there are a lot of examples like this in these cosmological simulations. On the other hand, on the side of the real data, when you have a simulation, you want to add all kinds of observational effects on top of your simulation to make it as close as possible to the real data. But even this part, it will never be able to do perfectly. So in astronomy, for example, we add a lot of observational noise, so make things look very blurry and ugly compared to these here. And there is actual blurring. For example, the telescopes do that, and you have to simulate exactly how this particular telescope blurs the images. So you have to add all of that. But even that is, of course, imperfect. And on top of that, you can have all kinds of problems with the detector. Maybe part of the chip isn't working perfectly. That's not in your simulation. There may be transient effects and all kinds of other weird phenomena. So yeah, there might be just a plethora of reasons why these are different. And then here at the bottom, I'm also just mentioning that, of course, the domain shift happens, and maybe it might be even more extreme, even in cases where you're not even dealing with simulated data, but maybe you have your old telescope and new telescope. You know your old data very well, so you want to start from there. But transitioning to new telescope means that you have very different pixel scales. You can observe very different objects. Maybe you can see fainter things in there. So there's like even more of a difference between the data sets. And again, this is a very common situation. This is also what we very often want to do. So yeah, so you can see there are many problems, but let's kind of go through how we would train a supervised learning model in this kind of scenario. And this is an actual example from some old project that we did where we were actually trying to classify merging and non-merging galaxies. So we want to find these rare, interesting, interacting galaxies. But compared to regular galaxies, of course, they are rare. So we want to have an automated method that basically discovers them easily. And so to do that, we, again, extracted these galaxies from a simulation, and basically we train a simulated model on simulated label data. And you have, it's a simple task. We have two classes, mergers and non-mergers. That's it. We're using a CNN, obviously, because this is an image-based problem. And in this case, this particular model basically decided to look at the peripheries of the galaxies. So in the middle, these like kind of bluish greenish plots are actually grad cams. So they're basically highlighting the pixels that were important for this classification. And so for the merger class, for example, the model always started looking at the periphery of the galaxy, which is, to me at least, kind of logical, because like interacting galaxies usually have clumpy, weird asymmetric structures at the periphery. And if the model finds that, then it decides that it's probably a merger. So it was pretty good at doing this. Of course, accuracies in this kind of setting are never 99%. It's like 80 is like amazing. So this is what we're trying to get. But if you want to then apply this model to a real observation, let me show you how a mock of an old, very big survey called the Sloan Digital Sky Survey looks like. So this would be the clean image without us making the mock, but this would be the same image with all the observational effects. So obviously, in this case, the model, if it's looking at the periphery, there's nothing useful there. Like everything was kind of basically erased by noise. So the model would, in this case, very obviously fail. Like you would assume that's going to happen. What internally happens, right? The model learned to place the features of merging galaxies in one area of the latent space and features of the non-merging galaxies in the other area. And there is, right, some kind of decision boundary between them. But as soon as you introduce an image with different types of properties, the learned convolutional filters do not work for that type of data anymore. And so the model starts translating these images into the latent space in a wrong way. So things can happen from like things being slightly shifted or moved around, like here in this like kind of toy figure, but they can be also completely messed up. But ultimately, whatever happens, the old decision boundary does not work on the new data anymore. That's obvious. So we basically need to find a way to modify the training to perform domain alignment, so that if we have the simple classifier, no matter where the galaxy is coming from, simulations or real data, mergers are always in one area of the space and non-mergers in the other. That's it. So how do we do that? How can we solve this problem? So this is a very broad area of research in AI, and I'm sure if you've ever thought about this problem, you've seen a lot of papers on this topic. But ultimately, the main goal of all of these methods is basically trying to modify the training in some way to enable the model to find robust and domain invariant features. Meaning, can we find features in these galaxy images that are still present in both data sets? If we try and find those and use those, and ignore those that are kind of different between the two data sets, then we will build one model that can actually work on both data sets at the same time. So this is kind of the main goal. But a specific situation where you might want to use something like this is a situation where your target data, so the data set where you want to apply your model, is actually unlabeled. So you can't fine tune the model on it, or maybe you have very few labels and that's not enough. So you only have the data. You don't have scientists who have pre-labeled anything for you, which is in reality mostly the case. So this is why we need something else. We need to find a way to utilize this other data set without any labels. And as I said, the types of methods that do this there are really a lot of them, but I like kind of distinguishing these three groups. One being distance-based methods. That is a huge group of methods, but basically the idea behind all of them is, let's say in that convolutional neural network example. So once we go through all the convolutions and we get to the, let's say, first dense layer, if we think of that as our latent space, if we use the latent distribution of dataset 1 and latent distribution of dataset 2, and then add an extra loss that's some kind of distance metric between these two distributions, and we minimize that as an extra loss term during training, we will try to push these two latent distributions closer together and hopefully overlap them in a correct way. And once that happens, you can hope also that the model will perform better than without this extra loss term. So this is very specific. You have to choose what kind of domain, like distance metric you think would work for your problem. And we can talk more about this later, but generally speaking, depending on what you think your two distributions look like, you might choose one or versus the other distance metric, because as soon as you have a specific metric to minimize, you have to think about whether that's actually possible at all. Because like, what happens if the two distributions are very different? Maybe in the classification problem, you have one data set where you have abundance of class 1, but the other target data set does not have the same distribution of classes. Then you will be forcing something that's not very easy. A little bit more flexibility comes with these types of adversarial methods, where you basically are training with an auxiliary task, and you are allowing the model to do and move things around in the latent space anywhere it likes, as long as it does this auxiliary task well. So, and very basic example of that is here in the middle figure. This is called the domain adversarial neural network. So basically, the regular CNN that I was showing before, that CNN would only have the green part, the convolutional layers. It would have the blue, in this case, the blue branch that's, for example, classifying mergers and non-mergers. But in this case, we're adding this pink branch, which is also just dense layers. But this branch is going to try to classify whether the image is coming from simulation or from real data. And there is a trick there, which is this kind of white arrow there, which is gradient flipping. So basically, what we're trying to do with the pink branch, because we're flipping gradients, is to make this classification loss worse and worse over time. So because of that, right, you are forcing the convolutional layers to find features that are very crappy at distinguishing between source data and target data, so those two labels. But they are still really good for the loss in the blue branch, so classification of mergers and non-mergers. So you can see that there's no hard coded distance metric or something like that in this approach. You leave it to the convolutional layers to find those features. So you can move things around any way it's like. A similar approach would be the right side, the reconstruction-based algorithm. In this case, basically you're just substituting the pink branch, the domain classifier, with a reconstruction task. So basically both your source data and target data go into the top branch, which is classifying your galaxies. So sorry, only the labeled data is going to the top branch, which is classifying galaxies, because that's where you have labels. But in this case, the unlabeled data can be forwarded to the reconstruction part, which just basically needs to encode the image and decode it back. So you need to find features that are good at this reconstruction, but also for the labeled dataset classification. So you can see in all of these cases, the training basically is only using labeled simulated data or source images. And for the target, there are no labels. You don't need them in any of these extra tasks. You're not using them, so you can just train without any labels in the target. So in this simple example that I was showing, basically this is how you modify the training. You would have labeled simulated images and unlabeled observed images. You choose any of these methods that you like to kind of perform this domain adaptation. But what ends up happening is that from using, in this case, peripheries of the galaxies and any features that it can use, it basically learns that it has to focus more on the centers of the galaxy. So now the grad cams go from periphery to the center, because ultimately that's the only thing that's visible in the noisy data set. And so you end up with a model that can perform on both. This is also a plus compared to transfer learning, because the transfer learned model now no longer works on the first data, right? You have to have two separate models. But in this case, you really have one universal model that works on both. So if that's something that's an extra bonus for some specific application, that's also good. Let me show you how that actually looks like. So these were kind of so I'm plotting here a TS&E, so 2D representation of my latent space. And this is how the latent space would look like for a model that's not been trained at all. So this is epoch 0. I have not started training. The bottom part, these kind of see-through points in the blue ellipse, those are my simulated source images. The top one with the brighter points are actual real observations from SDSS. So this is this survey that I was mentioning. So I have, again, still two classes, mergers and non-mergers. And of course, everything is mixed. I have not started training. But because the properties of images are different, even these like randomly initialized weights already place everything separately, which is kind of interesting. So if I train just on the source data, so regular model, there's no domain adaptation. I just train on these simulated galaxies. You can see here on the bottom, so the blue ellipse is now on the bottom, I'm starting to differentiate between blue area and red area. So I now know in simulated galaxies which are mergers, which are non-mergers. And this particular model, as I'm writing here, had an accuracy a little bit above 80%. But because there's no domain adaptation, the real data is completely detached on top. It's basically randomly guessing what is the class. So it doesn't work at all. Instead, if I train with domain adaptation, this is how the latent space would look like. So basically, both types of points have their own red area and blue area, and accuracies are pretty good on both. Like in the target domain, we basically shoot up from 50 to 80%, so like 30% increase. So now, even though the galaxies do really look different in observations, we can still use this model on the real data as well. So this is a simple example, but of course, you can utilize the same principles on any kind of task, basically. You can just think of it, I want to make a better latent space, and then do something more robustly with it downstream. So basically, you can have one or more source data sets. You can have one, or I guess more also, target data sets where you want to apply this. You can, depending on the data, you can use a CNN, you can have a dense network or a graph neural network, depending just what your data looks like and what you think is best suitable for that. And then you apply your domain adaptation to the latent space after you do the encoding. And then the decoder can be dense layers, like in the example before, where you're just doing classification, but you can also maybe have more convolutional layers or something like that if you're doing data generation. So basically whatever you need can be the downstream task. But of course, as I was mentioning before, I mean, this can work, but if you start diving a little bit deeper into like why is it working and why was it failing before, that's kind of where like the problems start, because like we still don't really fully we can't really truly interpret all of these models as well as understand the uncertainties. So how does my, like if I have some kind of error bar that I'm predicting, how does that change when I use or don't use domain adaptation, and why does it change basically? So all of these like slightly deeper questions are something that I believe at the moment we can kind of only superficially answer. So I'm hoping, since everything is moving so fast in AI, then I will be saying a completely different story in like a couple of years. But with that being said, like I want to have just time for like a few slides on UQ, just because I want to just give you the story of like how people in science, at least, have been thinking about this so far. So in this context, I guess let's imagine that we have a simulator, so some simulation, and usually what we would do, right, we know what we want to simulate, we know how to do it, but we have to input some prior ranges for different parameters of the simulator into our simulation suite so that we can create a big data set with different range of properties. Once we go from these initial parameters theta through simulator, we will create our observables, our data, or in this case, X. And let's assume that we just want to train a neural network to go from observables X back to inferring these initial parameters theta. And so basically, let's assume that these are some numbers and that we literally want to do regression. Initially, right, when we were able to easily train neural networks, we were perfectly happy that we could do point predictions, because we can at least do these point predictions extremely fast once we're done. And in many applications, this is more than enough, and it's great, and everybody was extremely happy that we could do this. But after that, of course, for many applications, we also wanted to get some kind of uncertainty. So usually the first step was, right, we decided that we are now predicting mean and standard deviation for each of our parameters theta, knowing and understanding that maybe this, in this case, Gaussian assumption might not be a very well chosen distribution for this parameter. We could, of course, before I go to this, another, of course, option, it would be to do an ensemble of these, or do even a BNN, Bayesian neural network, where all the parameters in the hidden layers are substituted with distributions as well. So in some sense, you would have an infinite ensemble, so that you get a better sense of like internal parameters. How do these change the error bar as well? So what is the error from the weights themselves, and not just what you're predicting that your kind of the error bar on the parameter itself is. Of course, the next step, and something that's like extremely popular currently, I would say, in science in general, both, I think, I mean, I'm seeing a plethora of these papers in both astrophysics and physics in general, is simulation-based inference. But I mean, maybe you've seen this kind of name being thrown around there. The idea behind this is that you want to utilize some kind of more flexible method, basically, to infer parameter posteriors of arbitrary shapes. And people very often use something based, some models based on normalizing flows to do this. So because normalizing flow is just kind of a neural network that does invertible transformations that can go from simple to arbitrarily complex, in some sense, distributions, you can basically predict the actual shapes of the posteriors for these parameters. And if you're inferring more than one, you can also nicely see if there's some correlations or something weird going on and how they interact with one another. One thing that I wanted to advertise as the next step, because again, there are many issues even with these methods, of course, but the next step, in my opinion, and in general in my group, is even without us updating the methodology and making something even better than this, that we need to, this would be very easy, but it just kind of a suggestion, let's say, we need to try and start aligning intent and implementation of UQ a little bit better, especially in our scientific papers. This is actually something that you can read more about in this paper. This is a position paper that's basically advocating for epistemic hygiene, as how they call it. These are written by Trivedi and Noor, who are both in my group. But basically the idea behind this paper is that we already have so many different methods for uncertainty quantification, both from just pure math and statistics, but also as well as like things that are developed for like kind of in the AI sphere. But different types of error bars mean different things. And so depending on what your problem is and what kind of metric for quality you want to establish in your work, you need to find the correct choice of error estimation at the end. So basically, which is very often not the case in many papers. So we kind of need to clearly define the inference chain, match UQ with the context that we have, and also do a lot of more experimentation at the end. So check forward and inverse validity. How does your model perform? Does it go well both ways? If you're lucky to have a simulator that's quick, then maybe change the knobs in your simulator and see how your trained model performs so that you understand better what are the pain points. Is it stable? What is the error bar meaning? Of course, benchmark beyond IID, which is basically, what if you have domain shift in some sense? Like what happens with your errors in your model if your test set is not from exactly the same distribution? So basically study model stability. And sure, all of these sound very like obvious, like I'm doing this, but if you actually look at papers, you'll see that a lot of this is actually missing. So this is just me maybe saying, do this or read this paper, it's fun. In the context of domain shift, obviously, as I said, the IID thing is the main problem because all the errors assume that you don't have this problem with your test set, but once you do, you can have all kinds of problems. So even these most complicated normalizing flow-based algorithms, they have like very flexible posteriors, but as soon as you show them an out of distribution test set, all like kind of things can happen. So what happens very often is that they can become very overconfident, meaning the errors are not going to be calibrated well. They're still going to have very like smaller error bars than they should. So they would not properly grow their uncertainty once presented with the data set. That's not really what they were trained on. So basically the confidence and accuracy are not kind of at the same level. And yes, and then again, maybe many people doing simulation-based inference, they're not checking for this problem. And also, even though we know that their ultimate goal is to go beyond the proof of concept and actually apply their model to their real data, experimental data. So yeah, so this is maybe a little rant about where the UQ is currently. But in the last, I don't know, 10-ish minutes, hopefully I'll show you just a couple of different projects that we worked on to show you different examples of how the domain adaptation can help and what the distribution shift does to the performance of the model. So the first example is this one. This was done by a couple of different kinds of undergraduate and graduate students that are mostly at UChicago, but as well also at other universities. So the question in this project was, can we infer strong lensing parameters robustly from both simulated and real data? So strong lensing, an example of a strong lens are, for example, these two clean, so I don't know, rings that you can see here. So this is something that happens when you have two galaxies that are directly aligned towards us, so they're on your line of sight. And then the gravitational pull from this galaxy that's in front is basically distorting the image of the galaxy that's in the background. So instead of seeing a regular normal looking galaxy, because of this gravitational distortion, you basically get an arc, or in perfect ideal situation, you get this full circle that you can see here. But of course, how the actual, let's say, ring looks like depends on both the masses and shapes and brightnesses of these two galaxies, but also like their positions relative to one another. So basically, we want to infer these parameters, for example, where they are, what's their shape, and so on. And these are super important in general for us in astronomy, because we can, if we can infer this very well, we can actually learn a lot more about the galaxies, but also about how the universe evolves, because this effect allows us to see very distant galaxies. So the task here is simple. We want to infer a couple of parameters that describe these systems, and we want to train a simulation-based algorithm, so these normalizing flows that I was mentioning, on clean images, and then we want to try and test it on something that we've made as a realistic mock of a survey called Dark Energy Survey, or DES. So these like noisy, very ugly images on the right. Again, this is a very rare phenomena. So in most cases, whenever people try and train any kind of machine learning model for lensing, it's usually on simulations because there's not enough data from the real images. So how does the model, the latent space, look like if there's no domain adaptation? So we basically just train on clean images. In that case, we get this plot on the left. So we have two kind of detached distributions. The colors of the points in this case indicate one of the parameters called the Einstein radius that we're inferring. So there is a nice gradient of like large to small Einstein radii, but because they're still detached, the model will not be as good on this other, in this case, I think the orange on the left distribution. So that's the noisy one. On the other hand, on the right, you can see that if I trained and add domain adaptation, I can align them and have like nice unique gradient for this parameter. Let me show you this as well. Maybe it's a lot to unpack, but this is actually a plot showing residuals, basically the distribution of differences between correct and predicted value. So we want to have tiny, narrow distributions very close to 0, 0 in each of these plots. So we want no biases, and we want very small deviations from the true value. And in case of the clean images, we are looking at the pink curves. They're very tiny. You can see that they're very, very like narrow and very close to 0, 0. But the noisy images, if there's no domain adaptation, you end up with these big inflated orange distributions of residuals. And if you, on the other hand, do domain adaptation, then you are able to shrink them to these blue curves. Blue curves are almost as good as pink, which is great given that these are very noisy images. So I think I was pretty satisfied when we saw this. So yeah, so basically this is doable even with these very bad images. Another example, so this is a completely different project. This project asks the question, can we correctly predict cosmology, meaning predict how the universe evolves, so this model of how it's evolving, across different simulations. So if you remember at the beginning of my talk, I was showing the simulated galaxies. They were actually from this simulation called Illustrious TNG that's here in the bottom left corner. But other groups have made their own simulations as well. Like here you have example of like Simba, Astrid, and Magneticum. So these 4 boxes all started from the same exact initial conditions. But because different groups had different recipes for different things that we're kind of unsure about, or that are super computationally expensive, they actually slowly drift away from one another. So these orange blobs, they basically represent gas temperatures, I think. And so see that some of them are very warm and the other ones are not. So which of these is actually simulating our universe? Well, probably none of them. And so if you learn anything, train a model on any of these, how can you actually trust it when you apply it to the real data when you have no idea which one is closer to the real data versus the other one? So, so basically the initial test that we wanted to see is, can we at least predict from one to the other simulation? So if we can do that, at least we are closer, one step closer to actually going to real data, but that's scary. So in this case, we are basically getting the whole simulated box and getting all the galaxies in this box and their positions, velocities, and all kinds of properties. And we are encoding that in a graph. So here we will be using graph neural networks to do this. And so we're basically learning one graph for the box and then saying, what is this graph related to, what numbers? So what kind of universe is it? And in this case, because again, we are in some sense doing regression, we're inferring some parameters, we will use the graph neural network as an encoder. And once we encode it, we add domain adaptation to the first dense layer, kind of, which we can say that it's our latent space, and then basically do a couple of dense layers to do the regression task that we want, which is in this case, inference of the cosmological parameters. So here is an example of how this works. This is a first thing that we tried. This is a very short project by an awesome student that came to Fermilab literally for like a month. But it's still promising, so I like to show it. Hopefully we'll refine this and do this better. So in this case, I am choosing two simulations, Simba and Illustris. And so the top row of plots is training without domain adaptation. So in the first plot where you have blue points, we are training and testing on the same simulation, in this case, the Simba simulation. So we want to be on the diagonal, so true versus predicted, we want that to be correct, and it is. But if you train on Simba and test on Illustris, you get this middle plot and you're kind of offset towards lower values. Obviously, if you look at the latent space where I have two separate distributions, it's clear that this model is not going to be working very well. So on the bottom, we have an example of something that we tried with the distance-based model where if you look at the middle plot, so training on Simba and testing on Illustris, we have managed to move a little bit closer to the red line. So this is very promising. And in the latent space, we see a kind of common gradient and things are now nicely overlapping. So since this was literally the first thing that we tried, I'm very hopeful that we can easily make this better if we just have a little bit of someone's time to work on this. And the last project, I am not going to go into too much detail because this is something that was actually presented in this series. I don't know how many weeks or months ago, but I assume that if people are interested, they can go back and look at this in more detail as well. But this is a project by a graduate student that I'm working with, where he was basically asking a question: can we perform an automated domain alignment? Because as soon as he started working with me on domain adaptation problem, he was very frustrated that it's very finicky. So you have multiple losses and a bunch of different parameters, things can go bad very easily if one of these is incorrect. So what we did there is basically make a completely automated method where all the parameters, including the weights of the losses, as well as the parameters of the domain adaptation loss itself, those are all kind of trainable. And throughout this training, they will change quite substantially because obviously, and this makes sense, if you start from very different distributions, different types of parameters work best in this situation compared to later after like 50 epochs when things are already kind of well aligned. And sorry, here are a couple of examples. So from very simple shapes to colorful MNIST to basically real actual galaxies from two different surveys. So this model basically out of the box worked on any of these cases without us needing to choose the parameters for more or less anything in this training. Again, this is very promising and nice and easy to run. So if you're interested in that, you can also check this out as well. Everything is on GitHub and publicly available. So with that, I want to go back to my circle of doom and just kind of say that, again, there are still quite a lot of problems in many applications. And while we are definitely in the big data era, both for industry and for science, there are quite a lot of other problems we still have to work on. And the main shift is one that I like to think about on my kind of day-to-day basis. But obviously, as I said, interpretability and certain quantification are not there yet. I'm hoping that we can all together work on this and improve it. And then in the next year or next time I give a talk like this, I actually have really cool solutions for you. But with that, I will stop and we can have a discussion. Thank you.